some periodicity stuff, right? Period 3. Any question which asks you about properties of, various ions or atoms when you're doing comparisons in the periodic table, really the answer rests on two things. It rests on electron configuration and number of protons that are in the nucleus. So, we should check both of those things in order to try and find out what the answer is here. Okay? Because it's not asking us about just a simple trend, it's asking us to deduce something. That's the verb of choice. Okay? So, yet again, I'm going to say elsewhere, let's just work this out. Na plus, Mg2 plus. They're both next to each other, right? Back to this kind of messy periodic table. Alright, they're next to each other here. Okay, so they do actually have, very similar electron configurations. And because they form differently charged ions, they actually adopt the same electron configuration, which is 1s2, 2s2, 2p6, right? They both adopt neon's electron configuration. They do it in different ways. One loses one electron, the other loses two, but they do the same thing. Okay? Why is this important? Well, it comes in the explanation as much as anything else. Basically what we're saying here is the number of electrons is the same, right? So if you think about your GCSE model, which we don't really use to ever answer anything, but it's useful for explaining things sometimes, right? Both of them have this configuration where we would have called it previously 2 and then 8, right? When you do your GCSE, you learn about these concentric circles, and you can sometimes write them as numbers. That's basically just, a simplified version of what you learn at A level, which is 1s2, 2s2, 2p6. What I'm trying to get at is, if the electron configuration and arrangement of the electrons was the only factor, these two ions would have an identical atomic or ionic radius, right? They'd have the same size. But it's not the only factor, because they don't have the same number of protons in the nucleus, right? Sodium has 11, magnesium has 12, and that's the deciding factor, really. Same electron config, but different numbers of protons. If you've got more positive charge in the nucleus, that's going to make one of these ions smaller, and the ion that's going to be smaller is the one that's got more protons, which in this case is magnesium 2+, which means this is the only possible answer for the first part, which is going to be worth a mark. And if you put Na+, you're going to have blown it, right? Your explanation won't be marked. So the explanation is to do with what we just said, right? Mg2+ has more protons in its nucleus. And I've not looked at the mark scheme for this, by the way, but I'm assuming that we'll cover all the bases. Mg2+ has more protons in its nucleus, but the same electron configuration is probably what I'd lead with. And then just to be sort of belt and braces to make sure that, I'm covering everything, I'd probably also mention same shielding. There isn't any sort of difference in terms of the shielding. There are no sort of extra inner shells or anything like that. So again, one more thing I might even say, and I'm pretty sure that you don't need to say all this, but you don't know which things they're asking for until you look at the mark scheme, which, is a year after the exam or whatever, so that's pretty useless. So I would also probably say outer electrons more strongly attracted or something like that, because that's basically what we're getting at. Because there's more protons in the nucleus, but there's nothing else shielding them from the effect of the nucleus, they're more strongly attracted, which contracts the ion, reduces the size of it. So then, it's quite a lot of work for 2 marks, that. But like I said, what we're doing is trying to cover ourselves. Write an equation to represent the process that occurs when the first ionization energy for sodium is measured. This is a pretty standard question. Just have to watch out. That you don't neglect to include your state symbols. All right, there's your answer. I mean, mark scheme might have it like this as well, because it's perfectly valid to cancel out one of the electrons from either side and put it like that. Either is fine. Okay, so more period 3 stuff. These are pretty standard questions so far. There's nothing too horrendous about them. First thing is, don't ignore this. The graph's incomplete, right? If you looked at it carefully, you'd probably realise that, but you may miss it if you're being silly and you just get straight to the explain part. It says complete figure 1 by plotting the approximate first ionisation energy values for magnesium sulfur. So, again, they've not helped you too much here because they've just given atomic number. What you could do to help here is actually put the element symbols, because chances are when you learnt about this, you will have looked at the element symbols rather than the atomic numbers, and so your explanations will have centred on, well, what happens, when you go from magnesium to aluminium, and what happens when you go from phosphorus to sulfur, which the question then asks you about. So you're supposed to just know, basically, the approximate sort of shape of this graph. The actual values won't matter, because obviously the graph only has very indiscrete, it only has kind of very large grid lines on it anyway, and you don't have to know ionisation energy values, you just have to know trends. So the first part is magnesium should be higher than sodium and higher than aluminium, but probably not higher than silicon, so that's where I've put it. Phosphorus to sulfur, this is one of the ones where there's a dip. Now they've kind of covered themselves here and not given anything away by saying it's different, right? So you could easily fall for it being higher. But again, this is just something you're supposed to learn, and it's often given as a sort of connected graph. This shape should be familiar to you because it's what period 2 and period 3 both do, and actually it sort of happens in period 4 as well, although there's a bit of extra confusion there because of the D block. Okay, so possibly 2 marks, I guess, for doing both the values, and then 2 marks for the explanation. That's probably the most likely thing. So we don't need to talk about magnesium and aluminium. That's a very common, alternative question, and it might seem really excuse me, it might seem really patronising of me to point that out, but you'd be surprised how many people talk about the wrong elements because they haven't read the question properly. And I know it's a cliche for teachers to go, read the question carefully, but you're wasting your time, if you don't. It's only asking about the phosphorus sulfur dip. So I call this bit of information, I call that the PS dip, or the PS anomaly, something like that, and it's something that we explain. So you can help yourself again by thinking about electron configuration here. It's probably easiest if we do all 8 of the elements, and I don't mean in full. All I'm going to put is the location of the outermost electron. And the reason I'm doing this is ionization energies are often determined by relative locations of electrons. Okay? Now, the magnesium to aluminium dip is the one that's explained by a change in sublevel, right? So that's one we don't need to talk about. Then you have to remember, okay, well actually, phosphorus to sulfur, we're going from 3p3 to 3p4, right? So there is no change in sublevel. So instead it's something else. And you're supposed to remember about the idea that in the 3p sublevel, I'm not going to draw the entire diagram, but there are 3 orbitals, each of which can hold a maximum of 2 electrons. So if you've got a 3p3 configuration, part of your diagram would look like that. If you've got a 3p4 configuration, you've still got the same number of orbitals, and you'd still put these 3 in, but then you'd have a down arrow showing a paired electron. So that's what we need to arrive at, right? So the answer is sulfur has a paired electron Again, I'm going to be very specific about this because I don't know exactly what the mark scheme says. In its 3p sublevel, right? This experiences slight repulsion because relative to the phosphorus one, you now have a paired set of electrons in one orbital, so they're kind of in a closer region of space, if you like. So because they're both negative, they repel each other a little bit. So the phrase I use when I'm teaching it is I say it experiences slight repulsion. It's not a major thing, it's only a little bit. And I'd also say that lowers the amount of energy required to remove it. You probably don't need to say that, to be honest. But again, it's that kind of belt and braces thing. Because there's a little bit of repulsion, you don't have to supply quite as much ionization energy to remove it. And that's why you get this little dip here. Again, this trend can be applied to period 2 and it can be applied to part of period 4 as well. So don't be surprised if you don't get asked about period 3. That is the standard one. The most common thing to be asked about is period 3, but it could be period 2 or period 4 even.